Hey everyone, welcome to this Flip Friday lecture. So this will be for Friday, April the 17th. So we'll be in our exam number 6 in LRC 201 this Friday. We did not have a Flip Friday lecture moving into last week or closed lab 5 due to tech vision and some other issues. So we just skipped through that closed lab, remember, but we're coming back for exam 6 on Friday. So this is kind of the lecture material that's going to replace that day. I'm going to finish up some concepts here from generative networks that we talked about, generative adversarial networks, and then move on to diffusion a bit. And then I'm going to start a primer on contrastive learning that we will finish up in lecture on Monday. So it's kind of a half and half. I'll start out halfway in the middle of a concept, kind of mop it up, and then I'll start a new one and then end that again kind of halfway incomplete. But that gives us then the chance to move into that concept in more detail when we get back into lecture on Monday. So just a bit of a heads up on what we're going to do here. And I will post the vid link here right on the slot for 417 just once I'm done finishing up with this recording. So I'm going to flip back over to my slides now and start working on moving forward here on generative adversarial networks. So this is where we left off in lecture. And I want to bring up a couple of other key points about this before we move on, sort of pop the stack a little bit and see how this fits into what we've been talking about all along. So remember that our whole idea here was to try to learn something about what we called a latent space. You know, it's this idea that there's some sort of lower dimensional representation or vector space where things reside in, and we're trying to use that to be able to explore and create objects. The idea is we want to learn these mappings from the ambient space to the latent space, and one of the primary objectives for that is often to do generative modeling. So you also generate things by plugging in reasonable values from the latent space and then being able to extrapolate those out to the ambient space. It may be kind of abstract thinking about how a model might learn these kinds of relationships, but it is clear that if I was to give you this video, right, of the car moving around in the circle, and you just saw that car going around and around, and that's what you observe, and then I was to say, draw me a picture of where that car is at 30 degrees, you'd kind of know, I need to put the car over here, right? Or if I put it at like minus 45 degrees, it should be like right here. If I do it minus 90 degrees over here, or 180 degrees down here, and you'd be able to draw a picture of that, right? Just, in other words, it's a way, you have some sort of mapping that you can learn in a lower dimensional representation. It's really just this idea of the angle is all that's needed to reconstruct it. And we talked a little bit about how the autoencoder is a way to do that. The autoencoder can allow us to learn hopefully this lower dimensional representation. But it still doesn't mean that there aren't complex patterns, and squeezing down into a low dimensional latent space may actually be problematic in certain ways. We know that that's a lot of compression and might actually cause problems because we have to necessarily remove details. Doesn't mean the latent space argument is like false for certain situations, but we know we're going to be compressing down, and we don't know how much information we need to lose to still reconstruct things properly. It will vary from task to task, and it really does depend on the complexity of the information you're working with. So here, just a simple video with one car, but what if we use 12 cars, or 20 cars, or 500 cars, or what if it's all the highways in the whole world, right? It becomes a situation where whatever the equation is that would describe the dynamics and help you draw out the situation of understanding where all the cars are, it would still get very large and complex in many situations. In fact, it could be that the combinatorial set of things inside that space is actually even bigger than the original number of points or pixels or data values that you have. Latent spaces are typically seen as being lower dimensional than the ambient space, but it doesn't strictly have to be the case. And we'll just see that means that maybe there's a way we need to clean that up a little bit. But if we do use the typical autoencoder strategy, you have to enforce a lower dimensional latent representation, right? It has to squeeze through some kind of bottleneck. The reason for that is because if you just gave a network, the same width all the way through, or as the input, so the input size and then the hidden sizes are all the same width as the input, or the hidden sizes are larger, there's really not much benefit from that. The network will naturally just be lazy and solve the problem the easiest way possible, which is just pass the input right to the output, because the targets are just the same as the input data. There's no real bias in the architecture of some kind to form a latent representation that's lower dimensional. So it won't really use those other data, right? It'll just map input to output. So autoencoders are limited in this way. We do have architectures then that also form these sort of bottleneck representations, the UNet or deep residual architecture. But again, what if that hidden space could be larger? These architectures could support larger channels in these deeper dimensions, maybe even higher dimensional spaces. But we know that an architecture that was given those additional channels, large high dimensional vectors for that latent space, well, they can't really use that because, again, it's just easier just to copy and use the copy connections. So how do we get models that can actually have these sort of complex latent space representations? Well, that's where the generative adversarial networks come in. So I'm coming back to this point now, right? Generative adversarial networks actually give you the ability to adapt the latent space to your desire if you want it to be high dimensional or low dimensional. Why is that the case? Well, if the whole objective here is to try to have a generator network that accomplishes this process, our input vector z, we get to set the length of those representations, and then it's trying to produce this thing that's well structured on the output. And notice, like, I don't give any constraints on the size of the vector z. It probably is that the digits exist on a low dimensional space compared to the pixel space and the MNIST digits. There's not that many of them. There are 10 digits, and yeah, there's a lot of variation and everything, but still, there's probably a way to be able to use a smaller dimensional vector to be able to represent that space, just like we can use a single value to represent the car moving around in the circle. But that's not strictly the case. If there are complex relationships in the world modeling all images in all situations, maybe we need to use a higher dimensional input, right, that then bottlenecks and creates a smaller ambience thing, but that latent vector that contains all this useful information. This is possible with generative adversarial networks. You can actually use a high dimensional input, and that input is basically a latent space vector. The reason for that is because after you're done training the discriminator and the generator in tandem, and they reach this equilibrium where the generator is producing good digits, then all I have to do is sample a vector from my distribution, right? My vectors could be whatever size I choose, plug that in, and I get something out that looks like an image. So using large vectors there and allowing them to learn a high dimensional to low dimensional representation is possible. That's not possible with the autoencoder technique. So generative adversarial networks open up the possibility of modeling what are underneath complex mathematical phenomena, but they're actually just being observed through maybe a slightly a lower dimensional ambient space that we're actually able to observe. So it's a little bit striking how that's possible, but this is something that generative adversarial networks can do. And you do typically get these sort of higher quality outputs from these kinds of things. However, they do suffer from a problem. So this is the main problem with generative adversarial networks and this way of training. It suffers from a known problem known as mode collapse. So the idea here is that whenever you're trying to train on your data, we know that similar data points in the latent space, right, when this gets learned, in that latent space, those original vectors, they're describing the actual relationships between similar types of things in the ambient space. They're just doing it in the vector space. So that means that, again, vectors that are close to one another in that latent space should be representing similar objects, and vectors that are far apart, dissimilar objects. So we can imagine that the 1 and the 0s, that there's a pile of these things that are very far apart. The 0 vector is on one side and the 1 vector is on the other side. Of course, you know, the 3s and the 8s are nearby neighbors because they're close to looking like each other, but they're still, you know, further away from the 4s and the other digits like the 7s. But in this space, though, you can also imagine that all the 0s are basically close to each other because they look similar to each other. All the 1s are close to each other because they look similar to each other. There are groupings, right? And there will actually be 10 piles of digits, 0, 1, 2, 3, 4, especially if you give a large latent space, then there's lots of room in that space for these digits to be separated out and represent those groups. But since they are kind of together in that area, that means they sort of form what we call a mode. It's like a group of points in that latent space that all belong together because they're in that same region. And the idea is that, yeah, this happens and you'll have multiple modes inside of a latent space in most situations, right? So your data will sort of cluster out. It's like those are all the 0s, these are all the 1s or something. This example I'm showing you is not an exact mapping to the digits. I'm just pointing out that similar data items will be clustered in the latent space because those things look similar in the ambient space. That relationship is preserved by the learning. However, you end up in this situation now where when you are trying to train a generative adversarial network, it has an ability to solve the problem in a lazy way. It's not the same kind of laziness I was talking about before with the autoencoder, where if you had a high dimensional latent space, it just doesn't have a bottleneck, and therefore it can just try to copy the input to the output, right? Only the bottleneck would prevent that from happening in that particular situation. In this case, the danger that you run into is that the objective itself is crafted such that you really don't have to find all of the modes in the data. So you can imagine the discriminator's job, its only job, is to be able to tell the difference between whether a particular image is real or fake. It doesn't really have any concept of what the digits are, 0 through 9. It just sees data that are images. And as long as it can actually label each of the fake images as fake and label each of the real images as real, then it has minimized the loss. It has brought the loss all the way down. It's getting those correctly, accurately assigned. The accuracy is up on that fake and real assignment. The network's basically done. But the generator could have taken a little shortcut to make that happen. So you can kind of see what I'm getting to here if you look at this image on the left. Basically, this is an example from a generator that's trained on MNIST, and if you look at the types of outputs, notice these are randomly sampled vectors in the latent space. Normally you'd expect all 10 different digits to appear, right? 0s through 9s, because it was trained on 0s through 9s, right? But unfortunately, the generator has decided to basically collapse on 0s and occasionally some 8s. You can kind of see an 8 that shows up from time to time, or an 8-like object. But most of this is all 0. And the idea is that the generator has taken a shortcut to just make sure it can produce really high quality 0s. As long as it does, everything that comes out of there, even if these are fake, the discriminator can't tell the difference between whether that's a real 0 or a fake 0. There's no reason to generate other digits, right? The generator can just generate 0s from now until the end of time, and the discriminator never has any improvement in its objective because it's basically not able to do any better than chance at figuring out whether these are real or fake. So the idea is that we wanted to represent 0s through 9s in our latent space, but what we have is everything is collapsed to a single mode. It's all 0s only. The mode being just the group of points that represent 0s. It never bothers to use the space to represent anything else. It can just get away with this shortcut of generating a 0. So the idea is, like, how do you prevent something like this, right? This is actually a really troubling problem with the generative adversarial setup. The fact is that the discriminator is not set up in such a way that different modes could be produced, and that can make it trouble to use. Now, there actually are ways to fix this, and if we use label data, like we actually have the data that is labeled, and I'll show an example of that in class when we get back on Monday. But I don't want to spend time on lecture today doing that. But in this form, as we stated it right here, which is the typical plain generative adversarial network, there is nothing in the generator to prevent this mode collapse problem, and that's an issue. We want to be able to deal with that. So we basically fixed we had a low dimensional latent space representation with autoencoders. Those were interesting, but we also noticed that we could have even the variational component, right, allowed us to make easy sampling so that we could use it as a generative model. But we noticed that the representations are fuzzy and low dimensional with the autoencoder. Okay, so we want to fix that. Generative adversarial networks emerged. They fixed that problem. You do at least get like real looking images out of that. But those real looking images, though, are often like hard to produce because you end up with mode collapse. And in the MNIST data set, it already happens. For more complex data sets, it's just even more likely to happen. The more modes or different kinds of things you need to generate, why would the network bother to generate everything when it can just learn to generate a subset of those, and that ends up achieving its objective? So GANs, or generative adversarial networks, they always fall into this problem of mode collapse under this particular formulation. So on the other hand, we did buy a high dimensional latent space representation. We are able, in that particular case, to be able to potentially use high dimensional vectors or represent very complex latent spaces. And that could be of use to us in the future. So we got to decide how do we now move on to fix this mode collapse problem. Now for that, that comes to diffusion models. So diffusion models emerged in 2020 to be able to fix the mode collapse problem with GANs. But suppose it was a 6-year stint, right? 2014 to 2020, people made jokes about how many like grad student hours were kind of wasted training up GANs to try to get them to succeed. Sometimes you'd end up with great solutions that were beautiful and can make all kinds of interesting images, but they were inconsistent to train because the mode collapse problem would often show up. So we had to find ways to fix that. Now there were some sort of ad hoc methods, so I'm showing you on this slide a few different techniques that people tried to create to sort of fix the mode collapse problem. So that's what these images on the right are trying to show, is if you use some of their tricks, a regular GAN may collapse on the modes. Some techniques try to help a little, but they mainly just blur it. And then you have these techniques called VGAN and unrolling methodologies that will actually basically help keep these modes all separated. But these kinds of tricks, though, are not always consistent, better for some modes versus others, so for some data versus others. So even though it's still an area of research, in many ways people have kind of given up and instead switched to diffusion models, which largely fix this issue. So diffusion models, how does this fix the issue? Well, let's reflect really quickly on why we think there could be some issues in this problem in the first place, and this will be inspiration as to why this approach ends up working. One thing I'll ask you to observe is that during this particular transition from the generator's input of a random vector to this image, something you'll notice is that you started from a random vector and you've transformed that into some kind of useful signal. Now it is true that that random vector represents a latent space, right? It means something there in that space. Close by points represent similar concepts and further away points are dissimilar concepts. That's true, and we know this is the case, but we also know that what we're doing is taking something that is random and even potentially high dimensional and complex and transforming it in one full form to the ambient space. The idea being we're going from random to organized, right? Where something that makes sense and is orderly out there in the world. So notice that my pointer went away. I think Discord is again breaking on me. Let me fix this real quick and we'll get back to it. I don't know if they have limits on the time of my broadcasts or what. It's very strange. Okay, and we're back. Hopefully this is it. Let me see what we got here. And also make sure that this is like it is too. Okay, so I think I'm back. So we have a random vector coming in. It's being transformed into the ambient space, where in the ambient space it now has order and structure to it, right? We think of this as maybe being a random input, even if it is organized in that space, and therefore it's now creating an orderly output. But that's happening in one full step. That's a pretty complex transformation, moving from a random space to an ordered space. And the intuition behind diffusion models is that maybe we need to not do this in just one swoop. The idea is the complexity of that code of writing that function would be quite large to go from random to ordered. The idea is to break it up into a series of steps or stages where we would slowly move from a random representation to an ordered representation. But we need a way to do that, a framework for helping us to make that happen. So this is how diffusion models work. What they do is, first of all, we take an image, whatever images we're going to be training on, and the diffusion model ends up just being a generator only. You don't need the discriminator to be able to train this particular model. So it's just the generator alone, but the generator is special. It's a true U-net structure, which means that the input shape and the output shape are both the same. It is actually mapping from an image to an image. And that fits the architecture that we talked about before, like the U-net, very nicely, right? The U-net architecture allows you to have a mapping where you could have an image as input, and you have this potentially bottlenecked type of layers here, and then going back out to the same shape. But you could also keep these latent representations quite large in size if you wanted trying to represent a very complex latent space relationships inside of that network. Diffusion models accommodate all this, so they can deal with large latent space representations. They also naturally work with this type of U-net architecture or other residual architectures. The network cannot be lazy, and we'll see why when we look at the training objective in just a minute. But when you're thinking about this architecture, keep in mind that you do actually have an input size. So here, whatever the input is, you're also going to be producing the same thing on the output. So we actually start, in this case, when we pick our random vector, right? Our random vector itself is actually random values that are already organized into this two-dimensional, really three-dimensional shape, right? Because it's picked height, width, and channels, right? Or channels, height, width. And so we have that already 3D thing that we generate and fill that with random data. That would be a latent vector, right? It would be random data, you might say. But it's not really random, a random latent space, and I'll talk about that a little later. Before we get there, let's just see how we actually set up the problem itself to do this stage by stage, from random to ordered, right? That's what we're looking for. In order to make that happen, we actually take an image, again, so we're going to be training this UNet, right? The UNet needs to figure out a way to help create an ordered output. But we're going to make the UNet do a particular job for us. It's not really going to actually generate the image. And so I'll explain that, but first let's just see what we're going to do to be able to get basically the inputs and the targets set up. Because for any type of problem, you have to have a good set of inputs and targets so that you can train your model. So we start with an image, and what we're going to do is add a little bit of noise to the image. So this is actually like typically Gaussian noise. It basically mixes some of the pixels a little bit up. It's basically blurring the image in a way, right? But it's mixing all the colors and the signal all together and making it a little bit blurry. And notice it's just a small amount on each step. And we do this as a series of stages, this blurring, which is introducing random noise slowly into the image. So you take the original image, step by step you blur it through this process. We call this the forward process, where we're adding this random noise. And it really is just random Gaussian noise. You could pick other kinds of noise that you want to add to your images, but typically this is what we work for images. We call that the forward process. It takes the original image, slowly adds noise until eventually the image is completely destroyed. Again, it stalled out on me. Let me go back again. See if we can fix it here real quick. I'm going to have to pick a different tech here for recording next semester, because this is just not consistent anymore. Maybe they'll fix it, or I don't think it's internet connections or anything. I seem to be connected fine, so sorry for the troubles. But we take this image and we blur it to the point that it becomes completely erased, right? Just by adding random noise. And once we're done here, we really do have a random sort of vector that we're talking about. But we started with the original image, we did this forward process, we generated these stepwise, right, blurring processes. Now, what we're going to do with the neural network now is fix this problem. We're basically going to go in the opposite direction, or learn what we call the reverse process. So this entire set is like a set of transitions from the original ambient space to what we think might be a latent space. It's really just a random vector here at this point. But we want to say, let's clean that up. So what we do is we make sure that we have the network be provided with two pieces of information. It's provided with the image at a time step, right? But it's also being provided with information about what step in this process we are in, right? And so here we broke it up. We could count the number of steps that we have here. It's always fixed. It's always the same number. You're always adding the same amount of noise until you get to a random image. Any image gets like fully blurred when you get to these steps. You can set it up such that that'll happen for any image that you have, and it has a fixed number of steps. So you could think about these as almost being like position encodings, like where are we in the process so far, and those are being added in as input to the network as well. There's this kind of hidden here, right? But there's an additional input. What time step are we on? And the network's job as a UNet is to, instead of actually predicting what this next thing is, that may be your intuition, right? Well, it's just going to predict that next step in the time frame, right? It actually does something different. It's trying to predict, actually, given this input image, what is the noise that's currently in this image. So it output for this net, given the time step we're on, plus this noisy step that we're on right now, it takes that and produces what's called a noise output. It's the shape of the image, right? But it's the noise that was in the shape of the image. It's predicting that we were adding on that step. So it's trying to take and predict the noise that was added. Once you make a prediction about what the noise is, then you actually subtract that noise out of this image to create the slightly cleaner one. And then we move to the next step. Again, we plug in now we're on the next step. We have this new noisy image. The network predicts as output, even though it's receiving a noisy image as input, it's predicting for this step I need to clean the image up. I think this is the noise that I need to remove. It predicts the noise. You take the noise and you subtract it out of the image. You now have a slightly cleaner image. Again, you pass this in for the next time step, it predicts noise, you subtract out the noise, blah, 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 blah. Eventually, you're trying to reverse this entire process, right? And here's the thing, the network can be trained on this because you have the amount of noise that you actually generated on each time step, right? I know the exact noise vector that I generated to be able to update the image and create the slightly noisier version. So when I take this image as input and I provide and say it was on this time step, I can actually have a target that says this is exactly the noise that I added to that image. And so this can be trained just from the forward process data that you generated, right? So there's lots of steps, but each step you can train the model on all these different steps, and you just kind of mix them together into a training batch so that it's always running to map from random steps across random images, and there's a good shuffling process to make sure the model is learning how to do this well. You typically do it in batches of images and go through all time steps, but the idea is you need to have something that can do this for lots of images. So how does this work in practice then? When you get a new image, something where you want to generate a new image using this model, you only use images during training, right? You do the forward process, you train it on the reverse process, but now you have the generator created. How do you initialize it? Well, in that case, you actually literally just start with basically a randomly generated image, and you just proceed. And you don't know what kind of thing you're going to get, right? You're just going to get something that will look like the images that you were trained on. So whatever pile of images this data set was trained on, these forward-reverse processes, right, reversing that forward process, this network has been trained on lots and lots of images to try to do this. That network will allow you to do this step by step. You do have to do the full reverse process step by step. You start with that, completely blurry, just initial random vector that's in the shape of an image, and you use your network knowing that it's on that first time step to predict the noise, subtract that noise out that you predicted, and then go to the next time step, get the noise, and subtract out what you predicted, and keep doing that. So it's a stepwise process that's slower, that takes more time than what you have when you're working with a generative adversarial network, right? The generative adversarial network just goes in one pass through the model, goes from random vector to organized output. Here, you have to do this as a step-by-step process. And there usually have to be, I don't know, it depends on exactly the time step, but we've tried to do some optimizations to make it shorter, but some number of time steps, about 100 maybe. It depends on the exact task, the complexity of the data, there are hyperparameters that you have to adjust. But in general, you do have some stepwise process. So it takes longer to generate images from this type of model, not as fast, but what do you think? You fix the mode collapse problem, right? Because in this case, no matter what you do, right, the network can't be lazy and just only generate zeros, because you are actually seeing ones during the training process that are being noised up in the forward process, and then you're actually having to clean them up during the reverse process. So the network is forced to deal with the full complexity of the data set. You can also see that you start from like a high dimensional latent space. Like it's actually even in the original dimensions of the latent vectors, so it's likely that you're already starting from a pretty high dimensional representation. This is something means that you're able to stay in this high dimensional space. You're not trying to lower that in any way. So there's plenty of room to represent a lot of complex processes, and that's nice as well. So you get this ability to potentially represent high dimensional latent processes and also to be able to model them. And we really did see that you got a very good performance out of these kinds of models, and it started saving graduate student work hours to be able to train these compared to a generative adversarial network. So this is an elegant solution to the mode collapse problem. Now I do have some code on the repository, on the course website that I'll go through a little bit on Monday to look at what this does. And I've got one little detail that I'm going to add to that when we go through it as well. Because those codes I also have are a little special. I'll go ahead and talk about it here just briefly, but then I'll maybe look at the code, of course, in class. I just don't want to spend the time on here too much looking at the code. So one thing about this, though, is everything I've described so far is what's called unconditional generation. Unconditional means you're basically going to get something out that looks like the things you were trained on. So the diffusion model, for example, or the GAN for that matter, you start from a random input and you're going to have an image pop out, and that image looks like something you were trained on, but you have no idea what you're going to get. And sometimes we would like to have a little more control over that, to actually know, like, we're going to produce this kind of thing. So an example would be for the MNIST data set, maybe I don't want a mode collapse model, of course, but I do maybe just want to get a 3 out, right? But right now, the way I would have to do that with the GAN or the diffusion models, I just had to generate a bunch of them until I got a 3. And that could be a waste of cycles, right? I could generate a lot of other digits before I finally end up getting a 3 that I wanted out of this thing. And of course, with the MNIST digits, it's not too bad. You got basically a 1 in 10 chance. But for other more complex data types, you're like, I want to get an image of a dog out, but you've been trained on images of all kinds of things. It's going to take you a while, right, to be able to find that particular image you're looking for. We need some way to be able to kind of control this process, and that's what we call conditioning. Conditioning is really a simple process. It just sounds a little like it's not at first, okay? But there are simple ways to adapt the diffusion model to make it a conditioned diffusion model, in which case it'll generate a type of thing that you're trying to produce. So if you imagine, these are all like CIFAR 10-like images. Really, I think they're higher dimensional. These must be ImageNet images. The one thing about generating an MNIST digit is you could take a digit and you could noise it up until it's all just a random image. But what you can do now during the learning of the reverse process is you can also add in an additional input, very similar to how we just said, well, there's an input for what time step you're on. You can also have an additional input, discrete, gets mapped to a different embedding that just says what category of image or what class of image am I currently trying to clean up right now. So the idea is when the diffusion model's trained, yes, it gets the input image, it knows the current step in the reverse process that we're in to guess how much noise needs to be taken out, or what kind even of noise needs to be removed. But it also gets this additional piece of information, just one more input that says, what is that thing? So if I'm currently working on cleaning up a 3, I would add in 3, and it would have this embedding for 3 added into the representations in that network. You could also have any of the other digits, right? Whenever you are making the model learn to clean up an image of a particular class, you make sure that you provide this additional conditioning signal. Why is that useful? Because at the end now, if I start from a new random vector and I set that conditioning signal to a certain digit, then I will end up with an output that is that kind of digit. So it gives you some control over the things you generate. Now, there are limitations, of course, with the conditioning method. It's really nice and easy for simple categories like the MNIST dataset. There's only 10 types of digits, so there's only 10 little conditioning signals. It's nice and easy to sort those into those piles. It's something we could ask for. But if you do think about a large number of categories, ImageNet has 1,000 classes. Yes, you could condition it, and so therefore you could generate images from any of these 1,000 classes, would be fine. But of course, you're kind of limited to whatever number of classes that you started with, right? So there's no way to be any more precise than that. Like, you're always going to have a limit based on the human labels, right? It takes something that was unconditional, unsupervised, and turns it into something that's conditioned, but now has some human input, right? We had to actually label those images and put them into categories to achieve that kind of conditioning. So right now, conditioned models, as we talked about them, they'd be supervised, right? You have unsupervised if it's unconditional, and you just get whatever out of it that's random. You don't know what you're going to get. But if it's conditional, you had to use those labels that came from humans during the training process. That's what allows you to control the output process. So right now, it seems limited by human labeling and not such a good strategy. But we will find ways around that a little later on. But I do want you to keep that in mind. You can condition the model if provided with an appropriate conditioning input to create a kind of thing, and you control that process a little bit. Otherwise, you don't know what you're going to get out of an unconditionally generated model. It'll generate anything from the training distribution. Anything that kind of showed up in the training may show up in the output. And of course, interpolated values and other things in between, mixtures of things that seem to make sense, that seem to be like other people's faces who really don't exist, right? There's really not a person who actually there are people who look like these people, but they're not really people, right? Those are all fake images that we're looking at the top. But they look like real things because they have started from a random vector that got cleaned up. One other concept, though, that I have to bring in. The one thing that can be confusing here, though, is that I've talked about latent spaces the whole time, and the interesting and necessary almost condition of a latent space. So GANs help produce a latent space. They usually have those random vectors in the end. Wherever, if you pick a random vector and it's over here, it's going to be a 0, or you pick a random vector and it's over here, it's going to be a 1. There's some actual spatial relationships between those vectors. So you're randomly sampling, but you are actually grabbing something from the distribution, and it's organized in this way. So that if you grab another random vector and it's close by a random vector you've seen before, you're going to get something that looks like that thing, right? It's going to be usually have the same features in the ambient space, right? I have one vector that generates a 0. A vector nearby should also probably generate a 0. I have a vector far away, it's probably likely to generate some other digit because it's in some other mode in the latent space. So that happens for GANs. It happens for autoencoders. It's not true for diffusion models. So it wasn't exactly obvious when the papers were first published. People kind of speculated maybe there's a latent space here, and so these random vectors are somehow organized in a way. But the way the process works is actually the network will actually clean this up in different ways every time, because what you basically have here is there's actual randomness during the training process, and there's almost like pathways that you're going through in the latent space. There's more than one way to clean up an image as it's going along these paths. So the network, by definition, it does have something where you can deterministically control it, but it's not exactly working that way, because when you make small changes to the input, you could end up actually setting it off on a path that's completely different from where it started on. It kind of interacts with the rest of the updates and the noise such that you end up with a completely different image. In other words, if you take a vector and then you generate an image, maybe you get a 0 out, and then you take another vector and it happens to be close by in that starting latent space, you may not get a 0. You may get something completely different. It doesn't even matter how close that is, right? Only if it's exactly the same. Even little small values during that reverse process propagate through and create completely different things. The idea then is that there isn't really a latent space in that vector representation. The model also is not learning about how to make pixels in an image. It's actually learning how to predict noise, or something that you have to subtract out of an image. So it's really not even learning about the images. It's somehow learning about the noise that needs to be removed on stages such that things that emerge are organized and structured. So you are basically taking noise and using noise, and something is coming out of nothing when you do that, in a way. And there's a little bit of that's an interesting thing to think about. We don't have time to explore that much more or think about what the implications are. But the idea with the diffusion model is it takes randomness and then organizes it. By removing randomness from that, you get order, right? So something that has noise, subtracting out noise ends up with an ordered thing. Now that makes sense logically, but it's also not clear exactly, well, what is the order, right? How do you choose what the order is? And all I can say is it just comes from the data, right? Whatever order is in the data, that ends up being what the model is left with at the end of that noise removal process. And that's really interesting, right? Now, so what we're going to do is move on from here for a few minutes. I'm going to switch to another topic. But this kind of cleans up at least a little bit about diffusion models that we'll need to know for some other stuff that I'll talk about next week with contrastive learning. All right, so I'm going to move out, and I'm going to switch to the next set of slides, which is for contrastive learning. And I thought I had these. I did have them. Where did they go? Time series, biological. Interesting. I opened these up right before I started, and now they're not here. Import that. Maybe I just forgot to hit the button here to save it. Okay, so let's move on to another concept. We'll bring back some of these generative concepts as we start to round out the course. We'll start to see that a lot of things just keep intersecting and connecting with other things as we move forward. But we're going to move on to another learning paradigm, right? So we've been doing supervised learning in the beginning. We've now been doing a lot of unsupervised learning, or finding ways to train on data without having to have it labeled. We brought back the labeling a little bit with conditioning stuff, but we'll talk about that a little bit later. Contrastive learning is another type of learning that we can apply, and it has actually variants. Some variants of contrastive learning are supervised, some are semi-supervised and some are unsupervised. And we're going to try to focus on the unsupervised stuff first, just to give you some ideas about the power of this technique. But just keep in mind, contrastive learning covers like several different types. It doesn't fit neatly into one of these categories because it's a flexible framework that can be used for any of those other types of learning. So just to review a little bit, traditional supervised learning problems have this flavor to them where everything is involving a human label, right? And that particular target that we're providing is always provided by the human, and we use that to update our networks, right? And this is how it pretty much goes for supervised learning. Now, we can get around some of this with unsupervised learning. So let's give some examples of unsupervised learning. One thing we could do is like PCA, which I talked about as being unsupervised learning. Leave out those yellow targets, right? Just use your feature vectors here on the left, and then you create the PCA through your, this is like represented by a function here, right? This would be a neural network, but we're thinking, well, if we do PCA there as my function, it produces some points right here on a two-dimensional space that we can visualize. We can then bring in the labels after that learning process and just color our results and say, is it doing a good job of separating things? And for some types of data, like the iris data, it's a pretty good job. MNIST data, not as good of a job. We know that linear techniques may not be so good, so let's replace that little function that we have here with TISNI, which we looked at before, and that's a non-linear technique that's also doing a low-dimensional projection. That's also an unsupervised learning algorithm. And we use that and we get this labeled projection here, which does a better job of separating things. But of course, unsupervised have their limits because they don't have access to those targets. It seems like they're not as strong in a certain way. But there were some ways of constructing unsupervised objectives that were becoming quite powerful in the years after the transformer. One we already went through, which is the generative pre-trained transformer. All right, I'll bring that back here right now as that point because I'm on it now. But the generative pre-trained transformer is an objective that's unsupervised that you could train a transformer on, as long as you apply causal masking to make sure that that transformer cannot attend to future tokens and only uses past up to present information in the input to predict the next token. This ends up giving some pretty interesting capabilities at generative creating things, right? Modeling. The same way a diffusion model is used to generate images, you use a GPT to generate text. Right? It just requires that you do provide some kind of prompt of some kind, right? Some ordered input to start, and then you generate the ordered input that would follow. So it's a different kind of generative modeling, but it's still generative modeling, right? And it is unsupervised. You don't have to have a human in the loop to build that kind of model. There were some others that were made with transformers, not as common anymore, but still useful for certain tasks. So what I'm showing you on the lower left is a model called BERT. The training objective is that we're trying to build a representation, kind of like an autoencoder. It's a latent space vector to represent the meaning of words and sentences or the whole sentence as well. And you can use the type of BERT-based method to do this, and it's important because surface level features are not always what's important in text input. So for example, if I have a sentence that says money in the bank and, I guess what that's, I don't remember what this says here. Something, walk on the river bank, right? Money in the bank or walk on the river bank. Bank shows up in both of these two sentences, but they have two different meanings depending on the context, right? Money in the bank is talking about things that you can spend and use for currency, while walk on the river bank is talking about a place where you can sit down and like eat your meal or something like that. They have different meanings, right? Even though on the surface they're spelled the same, use the exact same token, they have two different meanings depending on the context, the other things that are around them. So the vector encoding for that token, like the embedding space, it needs to be different based on the context that it's in, not just its input features. So if you want a model that can model a network that can understand this contextualized relationship, you can train it in a BERT-like approach. And what that means is you basically mask out some piece of the sentence and you use the other pieces of the sentence to predict what those missing tokens are. And you do this many, many times over and over again, and eventually you get this contextualized meaning, where when it actually looks at these other tokens, it knows what would go there. It's able to treat those as having a different meaning when they're in different contexts. I'm putting this here and just going over it quickly because we may talk about it a little bit more in class later. BERT models are used widely still in natural language processing. They're basically used to be able to encode text into a vector space where sentences that have similar meaning are close in that vector space and sentences that have different meanings are far apart in that vector space. Kind of like we were trying to do with the encoder's context vector, but it's not for machine translation. It's just trying to build an embedding so that you can have sentences represented by vectors. Sentences, words, these sorts of things. It's just another example of an unsupervised training regime. What does that mean? It's unsupervised. You don't need a human in the loop. I take a sentence, I mask out or block out, pull out that word bank. I use these inputs, money in the, and then have the model predict bank. I do this randomly too. So maybe I do money blank the bank or blank in the bank. I do all these different forms and train the model over different permutations. So it's augmented in this way. It's not just seeing the same thing blocked out every time, but it's using this over and over again. That latent space vector that comes to represent the sentence then has learned all these different permutations of context and can contextualize these words and meanings correctly. So it's a way to do that in an unsupervised way, and it also can be used across multiple languages as input and is still widely used for building embeddings for languages. So we'll talk a little bit more about that later because there are some potential uses there. But these are all unsupervised learning problems, right? So in comes contrastive learning. I'm going to give you basically the primer here in just a couple of minutes, and then I'm going to wrap this up, and we'll talk about this more in class when we get back on Monday. But contrastive learning, this is in 2020, is a major shift in terms of learning. Okay, probably one of the biggest shifts that I've ever seen. Because we'll talk about the implications in class more. Right now I'm just going to go over the very bare bones understanding about how the process works and how it is like an unsupervised objective. So what we want to do is find a way to learn these vector relationships for images, right? So the idea is that, okay, in a latent space, right, images that have similar content should be close, and images with different content should be far apart. And we can use methods like BERT to do contextualized representations, but there's limitations to that, right? And that doesn't really become apparent until you start looking at what contrastive learning is doing, and then you start to understand why it might be limited in certain ways. So what we do is we have images, okay, that we put into these things. This is an image encoder, but we want to build an embedding. It's a latent space representation, same way we try to do with autoencoders and other things, right? We want a latent space vector that represents that. The reason is because latent space vectors can be useful, right? Just like we have a vector space representation of the iris data where we can see differences and draw decision boundaries. Once you have the data organized in a latent space, it might be easy to be able to classify and make use out of it. These sort of unsupervised techniques get the data ready for an easy classification task after that. So this is the same case we would always use for this. So let's see what we can do here. What we take is a model. So here's the input X. This is an image X. We take one image in and we process it in two different ways. What we do is we decide on a particular augmentation of the image, and one augmentation goes down one branch and another augmentation goes down another branch. So some potential augmentations are kind of shown over here on the left. These are some possibilities. So what we do first of all is we pick a random crop from the image, right? So we say random crop A. So that's a crop we take out of the image, right? And then we do another one. We take another random crop. So different size, different places, locations. This is data augmentation at work, right? It could be anywhere and of different sizes. And maybe we end up with crop B, okay? So that's what we do. Now, the important thing is we're not actually just going to use one image. We're going to do them in batches. So we have more than one image, right, that usually goes in during machine learning. It's not just one image at a time. It's multiple images. So we're also going to take not just the image of the dog, but also the image of the snake, and we apply the same, right, these. And we do the same for these, right? They all get cropped in these two different ways, right? So they get that region removed and this region removed. So in that batch now, all of the small patches, they go down the left side. They go through a neural network that then compresses that down to a latent space representation. Think of a bottleneck convolution neural net, right? Goes down until it squeezes away all the 2D information, and now you're left with a latent space vector. You do the same thing over here on the right. The bigger patch B, right? This is a bigger one. It goes down the right branch, and it ends up going through and it ends up producing a latent vector for that. Now what the objective for the network is not, its whole job is to try to figure out how these two representations agree with one another. The idea is that it needs to be able to correctly predict that the A and the B from the dog image came from the same image, that the A and the B from the snake image came from the same image, and that the A and the B from the plane image came from the same image. And importantly, at the same time, it needs to know that the A from the dog image did not come from the pair with the B from the snake image, and the A from the dog image did not pair with the B from the plane image, right? So there's something that we call positive pairs and negative pairs that get there, right? We know that the A and the B for the dog are positively paired, right? The A and the B for the dog image go together, two different crops. But the A and the B from the snake image are a negative pair, right? The A coming from the dog and the B region coming from the snake, they do not belong together. So what is this like? It's like when we take those three images, you basically are comparing them, and usually via dot product. Okay, we basically take the dot product between these representations and we say how much they agree, and we apply, a softmax function to say for the A, how does it agree with the three other B's that are on the other side. So there'll be a probability that it agrees with the dog B, and the probability it agrees with the snake B, and the probability that it'll agree with the planes B. There's three comparisons there. And what that is saying, which one do I guess that it is, right? And we know that the target is that A goes with the dog, right? Likewise, though, for the snake A, it should have a positive pair with the snake B, but negative pairs with dog B and plane B. And then finally, you've got planes A region gets negatively paired with the dog B, negatively paired with the snake B, but positively paired with the planes B. The idea is that all those comparisons, the probability distribution should be that it's, the dog matches with dog 100%, the snake matches with snake 100%, and then the plane matches with plane 100%, and you should have no alignment to the other. Those are negative pairs. This is the target matrix for that batch, where basically the target vector is 1, 0, 0, right? You should match the dog, but not the snake and the plane for the A stream for the dog. But then the B stream is like matching on the snake, but not on the dog and not on the plane. And then finally the other one is, well, we're not going to match on the dog or the snake, but we do match on the plane. You then also take this matrix and you adopt products and you transpose it and you calculate across the other dimension, matching B's to A's, and that gives us two sets of contrastive loss. It means these multiple calculations of cross entropy loss that we just average together. Now, it's not clear why this would be useful based off what I've told you so far, okay? But you are building a network that can embed images, and it can do this positive and negative pairing. And it's important to think about the fact that it's a batch of images that are going through at a time. Normally, during learning on deep learning, when you pass a batch of data in, each of those data items is processed independently. We do it at the same time just to do it in parallel so that we're able to just take care of parallel processing, take advantage of that, the fact that they're all reusing the weights during the batch. But in this case, not only do they reuse the weights, but they actually are used as part of the loss comparison. And there's interesting kind of effects that can result from that, and that's the implications of that are what we're going to talk about on Monday. But I wanted to kind of introduce the concept here now, just so you can get your mind thinking about what's going on here. So this is where we will start when we get back on Monday. I hope you have or have already had a pleasant weekend, and I will see you for the exam on Friday.